Hi everybody, thanks for joining this session. So this talk will give you a status on the work that Etienne and I are doing to make an SCMI server running in a trusted environment. So we have worked on this. So we are working with other people, but for this part, it's mainly Etienne and I who have worked on. So the goal is really to put an SCMI server in a trusted environment. And we'll go through what we have done so far and what still remains to be done. There is also a lead project tab on the Linux website where you can follow our activity. During this session, so yeah, we'll explain why we want this T, just give you a kind of background, and then which kind of typical design we want and why we want this, how we have implemented that in Opti with the Opti services, what we have right now, what are the next steps for I would say the next 6 months, and which are the other steps in the, I would say, in a far future or in the future in a more long time. So let's move first. Let's move to the reason. So why do we need an SCMI server in a trusted environment? So on SOC, we have more on the SOC are more and more complex, and we have more and more resources which are shared between the secure world and the non-secure world like Linux. And usually you can use a dedicated power coprocessor to manage these shared resources, but in some case, you also have to share the communication with this power coprocessor, or you don't have power coprocessor because of the size of the die. And in this case, you still need to make sure that the non-secure side will not overwrite or the configuration or the request from the secure world. And because the secure world is the one that must have the ultimate decision, we have decided to implement this SCMI server, this backend in a trusted execution environment. For this, our goal was mainly to reuse what was already done. So typically, we have the SCMI server running in a dedicated power coprocessor, but we wanted to reuse the software which have been already developed for such a configuration, at least to maximize this reuse. So that's why we decided to start with the SCP firmware, which is an implementation of the SCMI server, which have been done to run on the Cortex-M on a dedicated power coprocessor, and which mainly use the hardware mailbox. So that has been our starting point in order to reuse most of the software module, and also that will ease the configuration, because in our solution we want to be able to easily move the SCMI server in different place of your system. So that can be in the power coprocessor, or in a secure trusted environment, or in other place that will go further after that. So we can start by describing the typical design. Maybe Etienne, you want to present this typical design?
Okay, hello. So here on the diagram, we can see on the left side, which is the usual Linux kernel, which handles several drivers for resources. And among these drivers, these are resources that are not accessible straight from the Linux kernel. So this goes through this SCMI framework. So we have drivers like clocks, power domains, and so on. that interact with the SCMI framework, interacting with SCMI transport layer. And currently it's using shared memory. And the typical design we have that currently exists and is embedded in platforms is when this SCMI framework through the shared memory goes to the most right side, where you have a power coprocessor that handles all the SCMI services and receives this SCMI message through this mailbox. So here the intention is when we have the SCMI server acting on resources that are owned by the secure world. So here, typically in OPTI, the SCMI server would be implemented inside the OPTI, going through an OPTI interface, which here is depicted as an OPTI service. So we'll come back to that later. So here the typical design is that we have on the left side the SCMI client, that's called an agent, that communicates with the SCMI server in the trusted OS in the OPTI. And this is the part we're working on, and as an extension, and what we'll look for the future is that even this OPTI SCMI server could also itself interact with some external entities as a core processor, which owns its own SCMI server, or even another dedicated processor as the one pictured on the right bottom side for some specific resources that are not maybe dedicated to power, but still must be accessed through the SCMI resources. And so all these SCMI servers will communicate through some SCMI transport layers, as we said. And currently the one implemented in the coprocessor is the mailbox one. When we embed the SCMI server in the OPTI side, then we would use the OPTI shared memory and the native OPTI interface to reach the service and get the SCMI request being processed. So when we go through an OPTI, this means that the Linux kernel goes through some secure monitor, which is represented here as the EF3 firmware, or a secure partition manager. In the case of an OPTI, it could be a TFA running an OPTI dispatcher that allows the Linux to reach the OPTI. And so in the end, this SCMI server really acts on the hardware resources that could be clocks, power controllers, even deported on the PMIC through some links. So that's the big picture of what could be done and maybe extended. And I know that in the next session presented by Suvik Chakravarti on SCMI being embedded, he will extend also how this can be used in other environments. So in our case, we're considering as a first step the Linux kernel interacting with the OPTI. So maybe we can move on to the next slide that presents maybe where we could have SCMI servers and where we can integrate this secure SCMI server. So here, this picture presents only the server part, meaning that the client, the agent, would be, in our case, in the Linux kernel. It is not represented here. So what exists is what Vincent drew in green, which is the SCMI server in the power coprocessor. What we're working on is this SCMI server integrated into the OPTI trusted OS that is available. And what we're looking for in the more distant future, let's say, is maybe the possibility to embed this very same SCMI server, at least this implementation, in other environments as a secure EL1 that would run straight over TFA when there is no OPTI, or maybe in a specific secure partition when considering the latest works made on the secure hypervisor by Armen Linaro. or even the SCMI server could be hosted into the secure world of trusted firmware M firmware. And another possible setup would be that in the non-secure world, there could be several virtual machines, and one would act as an SCMI server to get all the requests from the other virtual machines, non-secure virtual machines that act as SCMI clients.
Yeah, maybe I can add. So yeah, on this, our goal is really that the same SCMI server can be used in each and every context, and mainly the goal is only to change the communication channel, the transport layer, because we can probably use different way to exchange the SCMI requests according to which context we are running, and also then only the really low level, the connection between this server and its environment, which can be typically how to allocate some memory or how to manage some interruption of some event. But the goal is really to have the same server. That's already what we have right now. So we have in Opti. As an example, we are able to run the Opti version of the SCMI as a Linux application in order to speed up a bit our development. But that's really the same. It's only the low level that change. That's really what we have focused when we have selected the SCP firmware and when we have worked on adding the Opti support. So the next step, which is the current status on our SCMI server in Opti. Do you want to continue, Etienne?
Okay, yeah, maybe. Okay, so when we consider integrating the SCMI server in an Opti, then we must have a transport layer, a way to reach the Opti SCMI service in a native Opti way. So currently this goes through some shared memory, as Opti already handles shared memory, and we can allocate some statically some shared memory, or even we have currently means in the with Opti for the non-secure world to register dynamically shared memory and then to allocate this piece of shared memory that will be used to exchange the SCMI messages. And going into the Opti, this SCMI transport layer should also invoke the Opti in the Opti native way, which is currently the most native way to invoke a service from the Opti is to use the invoke command interface of the Opti, which is currently based on the global platform T specification, where you open a session with some entity and then you invoke command into this session. So for this, we designed an Opti service which has this interface, which we call in Opti the pseudo TA, which are actually services in the Opti core kernel part, let's say, that do expose an interface which is a trusted application interface, like where you open such a session and then you invoke some command. So here, for example, the Linux kernel, the SCMI driver of the Linux kernels opens a session towards this Opti SCMI pseudo TA, and then when there is an SCMI message from some drivers of the Linux kernel that is requested, it triggers an invocation of the command into the SCMI pseudo TA of the Opti, so that the message is processed by the SCMI server in the Opti, and in the end, eventually acting on some hardware as requested. So this using this Opti, this allows us eventually to use several message or channels, or to define several channels, so that resources handled by the SCMI server can be decorated regarding this transport layer when those resources have no dependencies between them, so that a channel can be freely accessed even if there is a pending request on another channel, because both channel acts on resource that relies on specific hardware without dependencies in them. And so we work on creating those multiple channels using specific shared memories to be used for exchanging those messages. So we have some still some issues and things to address in the OPT, because when we create such a service in the OPT, since it's a system service, we must provision any resources OPT needs to run these services, so that we don't lack of memory or lack of T thread in the OPT when the service is executed. For example, we can imagine that non-secure client asks the OPT to access some data, and the OPT itself must ask the Linux kernel, for example, to access the file system or a resource. So the OPT goes back to the Linux kernel, and then the Linux kernel needs to enable a clock or to access hardware, an eMMC, for example. And if this very clock or the resource needed by the Linux kernel needs to be handled back in the OPT, we must make sure that all resources already allocated in the OPT for the initial request do not overconsume all the resources, and that there are still enough resources for the service to be handled. Otherwise, we may face some deadlocks. So that's a pretty rough overview of what's going to be done in the OPT. So we have currently a proof of concept, but there are still things that needs to be discussed with the OPT maintainers so that we get those resources provision maybe. Okay.
Yeah. Do you want me to continue on this?
Yeah, go ahead.
Okay. So yeah, so as Etienne mentioned, we have a proof of concept that is now running on the STM32 MP1 and on the FVP for ARMv8 and on Linux host for debugging. But everything for now is, I would say, out of the tree, out of official tree. So for the next couple of months, we will focus on backporting everything to the main repository. So on the SCP firmware, the mainline support, to make sure that the OPT, the modification that we have done to support OPT will be merged in the official SCP repository. So Etienne has already made some pull requests on some specification protocol, but the goal is really to have everything upstream. Also in OPT itself, as we are using this pseudo trusted application interface, we need to make our changes in OPT merge in the OPT repository. So that will be also a large work to make everything in a good shape to be merged. On Linux side, we'll mainly have to add the OPT transport layer, which now that the SCMI framework support multiple transport layers should be easier than before. And also in U-boot, that's something that is already under review. But yeah, we have created. We're already working on the SCMI agent in U-boot, which is using the SMC interface, and we also have to prepare an OPT transport layer, so we can access this server from U-boot as well. So that will be one of our main next step. And in addition to that, we also need to enable the notification to Linux. So the SCMI notification has been merged in kernel v5.9. And so with that being merged, we can enable the notification from our OPT SCMI server back to Linux, which will be mainly useful for sensor and power domain, for example, or reset as well. So that will be something we have started to work on, and our goal is to have something up and running during the next cycle. We're also working on supporting the voltage regulator specification, which is a new, which has been added in the latest release of the SCMI specification. So we have a proof of concept, if I'm not wrong. Etienne has worked on this, and the goal is really to make it back in the SCP firmware. And the last item is the support of the device tree. While working with the SCP firmware, the one main, I would say, issue or complex things to do is to set up the hardware configuration in this SCMI server. Right now, everything is based on array which are statically filled. So all the connection must be done and before compilation, which is sometimes a bit, I would say, complex and time consuming. So we will consider adding the device tree support in this SCP. So either to be used at compile time, similarly to what is done in Zephyr, for example, or even at boot time, so that we can parse the device tree blob. So that will be a main new feature that we would like to add. Not sure that this will be done during this cycle, but that's part of the plan, at least. I think we still have a few minutes. So that for the next, I would say by next step, we mean the next cycle. And then the other future step that we want to have a look at, it's extending the use of this SCMI server in other T. So either in the SCL0 secure partition when we are running alone with TFA, or in a dedicated partition once the FFA will be available and the hypervisor will be available in the secure world. We expect to take advantage of the refactoring that we are doing for Opti, so we can easily plug the SCMI server on this new execution environment. And I would say the last one, which this has also been requested by some of our members, is being able to run this SCMI server in the secure side of the Cortex-M. So typically around the TFM or something like that. But that's really something we have not really looked at for now. That's really for the future. And I think that we have covered all our slides. Etienne, do you want to say something else, to add one more thing? I don't know. I will check if we have some question in the meantime.
I've just looked at Slack and it seems there's no specific question.
Okay. That will mean that we have been crystal clear in our explanation.
Sure.
So yeah, we have 2 more minutes.
Okay, maybe just mentioning is that there are some Jira tickets that are publicly reachable for one to just follow what's done on the SCMI.
Yeah, on the website, Linear website, then there is a project tab, and there will be the SCMI project there, where there is card which describe what we are working on. Yeah. Maybe also one other thing to come back on, just that mentioning that this SCMI server in VM, that's something that have been recently added as part of the possibility, typically to be used as a backend proxy between some non-secure site VM and another SCMI server that could run in a coprocessor or in Opti or somewhere else. So yeah, that's we are keeping that in mind while working on our current activity.
Yeah, and follow the next session from Suvik. We'll discuss also about SCMI and what ARM envisage for the future use of SCMI.
Yeah, exactly.
Well, thanks to all. Thanks for attending.